Hi, everyone, and welcome to the last session of DOTS for the spring semester. So the first speaker of today will be Pietro Belotti, and he's an associate professor at the Politecnico of Milano in Italy, where he also received the PhD in 2003. After that, he went to the Carnegie Mellon as a postdoc, then he moved to Lehigh as a visiting assistant professor, and finally was an assistant professor at Clemson University. After that, he was a software engineer at FICO from 2013 until 2021, when he moved back to the Politecnico. And today we'll be talking about branching on continuous variables in convex MIPs.
Thank you. Let me just unmute myself. Thank you very much, first of all, for inviting me to give a talk in this series. Let's start. So as you can see from the title, this is probably heresy for a lot of people because normally in mixed integer optimization with a convex relaxation, you don't want to branch on continuous variables. But I'll try to convince you that it's worth doing it sometimes. We'll do it through two applications. The first one is an old, pretty well known application that support vector machines with a specific penalization term. We'll see some schemes for spatial branching that are akin to strong branching in MIP. And then the second application will be, I only have preliminary computational results there, but it's still worth looking at the spatial branching for that one as well. So let's begin with the first application. That's a pretty well-known problem. You have n points in d dimensions. We call them x. So unfortunately, this is data and not variables. And each point is associated with a label, and the label is -1 or 1. And you want to separate the points so that the ones with the label -1 are separated from the points with label +1. And the way to do this is by finding the arguments, the parameters for a hyperplane that are W and B. Those are our actual variables for the optimization problems. You would like them to be such that for every point with label 1, the inequality W transpose Xi minus B is greater or equal than 1. And the opposite happens for the points with label -1. So you could condense everything into this single inequality where yi multiplied by this violation is greater or equal than 1. Clearly, if you impose all of these constraints for n points, you would get an infeasible system. So what people usually do is instead apply a penalty term that is, in our case, for the so-called ramp loss case, is 0 for a negative violation, obviously, and then it grows linearly until 2, after which it just flattens out at 2. And basically, so that means geometrically that the objective function you want to minimize, the total penalization, the total penalty term, is basically the set of the total length of these tiny segments within the slab around the hyperplane you're finding. And you have to find that hyperplane, so you have to find those W and B. So if the penalty term is described like this, it's this ramp loss function, then it can easily describe an optimization model, which is nonlinear and nonconvex, by just adding up this penalty term across all the points, multiplied by a large constant, because for stabilization issues, you also want to make sure that the coefficients are not too big, and you do this by also minimizing the squared norm of the coefficients of the hyperplane. Before getting into the way that we were trained to model this problem, you just have to look at this formulation, because it just tells you that the only actual variables that matter here are the W and the B. So the parameters, the actual parameters of the hyperplane. The way we would model this, because of these non-convexities and the discreteness of the problem itself, is a lot more familiar to us, and it uses binary variables. So we have a vector Z of binary variables, one for every point. and another vector xi of continuous variables between 0 and 2, because then the penalty term is simply described by the second term in the objective function as simply the summation of all the xi's plus the 2, twice the binary variable corresponding to every point, summed up all on all points. And then the satisfying the computing the violation of each for each point is given by the first and only constraint, the only class of constraints, where we basically want the point to be classified correctly minus this term psi I minus big M times Z of I for every such point. The big M here plays an important role. This is the whole point about modeling the problem this way. We have a discrete set of a set of discrete variables, and we use the big M constraints for such model. Before getting into the details of what we would like to do with this problem, let me just change notation. And I'm sorry if I just introduce something and change notation, but this is going to be a lot easier later. So instead of using W and B as the fundamental variables of our optimization problem, we're going to use a single variable, a single vector of D plus one variables that we call G. And then the data will be condensed into a set of n vectors V of I. So basically the left-hand side of the fundamental constraint is simply given by the scalar product G times Vi. So that's the term we're going to use until the end, and this is going to be a very important parameter to estimate. Whose bounds we're going to try to estimate, especially. So let me rewrite the MIP that we are going to look at. So this is the objective function, the squared norm of the subvector of the first D elements of G, plus again the penalty terms that are given by the Xi and the Z variables. Subject to, again, the violation. So the term G transpose time Vi must be greater or equal than 1 unless you are allowed to violate the constraint, in which case you either have a positive psi or Zi equal to 1. And in that case, the constraint is basically relaxed. The fundamental thing here is that the big M, as all of you know better than me, are strongly dependent on the bounds of G. On both the lower and upper bounds on G, depending simply on the sign of the corresponding data point V. The tighter the bounds on G, so the tighter L and U, the bounds on the variables G, the smaller the big M's, and that will give you a better lower bound. So, which is very useful if you want to find an optimal solution in a short time. What I say this because in general the structure of this problem is relatively it's a bit strange, because it basically you have the coefficient matrix with the G variables. The G columns are very sparse, and then you have very dense. I'm sorry. So the G columns are very dense. The Xi and the Z variables instead correspond to very sparse submatrices. So the bottom line here is that, yeah, if you, given that the only alternative of branching will be on the Z variables, but branching on Z doesn't really have a big effect on the rest of the problem, because you only have an effect on whether you want to classify or misclassify or a single point out of the n points. And instead, the G, being very dense, might actually have a much bigger effect. So why don't we branch on G? Well, you might answer, well, because they are continuous. Why would you ever branch on continuous variables? Well, if we try to do this, then we would have to, first of all, select a branching variable, Gj, for some of the J's. And importantly, because this is a continuous variable, select a branching point tau between the lower, obviously in the open interval between the lower and upper bound on G. And then the branching rule would simply be Gj less or equal than tau, or Gj greater or equal than tau. That's a spatial branching. That's a branching on a continuous variable. We can't really eliminate a lot of the solution space because this is a continuous variable. So how do we find the best possible branching rule, and how do we use it? Well, we need to work on the model itself, and especially on the constraint that will contain G which is here, I just rewrote it by changing the position a little bit. But if you look at the fundamental constraint of the problem, you have the psi I plus the big M times Zi greater or equal than a term that is basically the violation of the constraint for point I. We need to find, in order to find the right value of the big M, Mi, a lower bound on this term G transpose Vi. And the lower bound is very simply given by looking at the signs of the data points and just by using the lower bounds and the upper bounds on the G variables, and we will find a value that is simply dependent on again the lower and upper bounds on G and the data points. So all of this is available at every branch and bound node. So let me just summarize this data. The lower bound on the product G transpose Vi is simply given by this Di transpose times Vi. We don't need to say a lot more about this. Now, I might have said already that Mi, the value of Mi depends very much on the bounds on G. And in fact, the right value for Mi is 1 minus this term Di transpose time Vi. If this value, 1 minus Di transpose Vi, is positive, otherwise it can be 0. So every time I branch on G, and this is the fundamental reason why I want to try spatial branching on G, every time I branch on G, I tighten one of the two bounds on a single variable Gj, which means I should get a smaller and tighter big M constant, which will give me a tighter constraint. Obviously, G transpose Vi has Di transpose Vi is a lower bound, which means that 1 minus G transpose Vi is less or equal to this value for the big M. And instead, if the possible violation is always negative, if this upper bound on the violation is negative, obviously I don't really need to say anything about the big M, because the corresponding variable Zi can be 0, which is good because I'm classifying that point correctly. So let's get a little bit more into what happens when I do branching on G. So when Gj less or equal than tau, then clearly this value, this term Di transpose Vi changes, because now I have different bounds on G, whether it's the data point is positive or negative, will simply change some of the coefficients in D. But I won't get into the math here. It just suffices to say that I will get tighter, possibly tighter big M's for both the left branch and the right branch. The most important thing here is that this happens actually for every point. So I might actually get n stronger big M constraints every time I branch on a single variable Gj. So actually, I might actually get a stronger bound by strengthening all the big M constraints, pretty much every constraint in the problem. This is not enough, because I would like to see which or what branching rule I want to enforce, which means I still have the problem of selecting Gj and tau. I'm not entirely sure which variable Gj I should choose and which branching point I should choose. But I could try to estimate, much like is done in strong branching from MIP. And I could say, all right, let's simulate branching using the branching rule Gj less or equal than tau and see what happens. Well, I would have to solve an MIQP with all the variables G, Xi, and Z. And if I wanted to be a little forgiving, I could relax the integrality on the variable Z, so that at least I only need to solve a convex QP, which is relatively easy. And the same I could do for the greater than or equal to branching rules. So I could solve two quadratic optimization, convex quadratic optimization problems, both continuous, for finding what I gain in terms of lower bound when branching on Gj at point tau. This is not very good news, but if I did so, then I would get a score, which is one of the possible scores to be used in strong branching, where I get the minimum of the variation in lower bound for the left branch and for the right branch. And obviously, I should adopt the branching rule that gives me the maximum possible score, and that will give me the right branching variable j and the right point tau. Um, well, this is in theory. In practice, what I would have to do in this case, because I probably have few variables, so d is usually small, but then I have many possible points tau to choose from within the interval Lj to Uj. So I might actually have a lot of quadratic optimization problems to solve. And actually, I would have 2d plus 1 times k if I chose to just sample the score estimates for k possible values between Lj and Uj. Solving at every single branch and bound node 2 times d times k quadratic optimization problems is not wise. I didn't try it, definitely, because I don't think it would make any sense. But I tried to do something completely different, which is the following. I simply said, let's get rid of G somewhat. So let's try to see what happens when I try to study the same problem, but I pretend that G is fixed. So if G, the fundamental variable of the problem, is fixed, and it's fixed in a way that it falls into the new bounding box triggered by the current branching rule, then let's see what happens. So let's suppose that now I use a G tilde that is simply given by either the current point that is found in by the LP solver within this node, and I just well, move it a little bit so that it falls into the well, the bounding box given by the branching rule that I'm studying. Then what I get is a slightly different optimization problem for both the left branching and the right branching. It's no longer that difficult because once I fix G were basically all the linking variables, and I don't have to do anything now because the problem is extremely simple. The problem is only in the variables xi and z, and given the structure of the problem, I simply have to, well, to find the xi I and the zi. But as you can see, the problem is decomposable, and I can simply solve all these n problems one by one. All such n problems are of this form. They simply have a slightly different big M at each constraint and a different right-hand side at every constraint. This is a problem in two variables, one continuous and one binary in principle. And this is binary because I could even restore integrality, because now the problem is so simple, I don't need to really do much more than this. It admits a closed form solution, obviously, which means that all of these delta tilde are now much easier to compute, and they give me obviously an estimate, so probably a very brute estimate of the real function I would like to compute using a lot of quadratic optimization problem. But the thing is, this way I get a very, very quick estimate, and I don't know if it's going to be a good enough estimate for the branching rule. Once I do this, well, the estimate score is again the same thing as before. So the minimum between what happens to the estimate when branching on the left and the what happens with the estimate with branching on the right, summed up over all the points. So it's very similar to what would happen in the true strong branching, only that the computation of delta I is extremely fast. So this is relatively easy to implement. Even if I take a lot of samples value for tau, I can get a pretty good estimate in very little time. The complexity of all of this is really O of k times n. And even if you have a lot of points in a large number of dimensions, this is a polynomial number of in k, n, and d number of estimates. So from a point of view of implementations, I implemented all of this, and every time none of the branching rules were good enough, in a sense that for all of them, the branching score was less than a given threshold, 10 to the minus 3. Then I gave up for those nodes, and I simply let the solver choose one of the binary variables to do the branching on. So it could easily be that some of the binary variables were still the right thing to do in those cases. Otherwise, if I actually found a branching rule that had a decent score, I first of all apply the branching rule on GJ using the tau that I just computed through the estimate. And I'll pause for 2 seconds because this is the most important point of the whole talk. Not only do I apply the branching rule on GJ, but I add also all strengthened big M constraints. I cannot stress this enough. And I wrote it in large font, in in bold font with a in red with with a box around it, because if you don't do this, MIP solvers don't realize what's going on. They see the branching rule, they probably think it's a silly branching rule. They don't strengthen, they don't modify the big M constraints. You have to do it manually within the branch callback. If you do so, then we'll see in a bit that this works. If you have to take home anything from this talk, please remember that if you do branching, spatial branching in MIP, you have a lot of extra work to do because you have to enforce every other strengthened constraints. So let's look at the first set of results. I used some instances from a previous paper I worked on with colleagues in 2016. These are relatively small instances with 100 points in 2 dimensions. And I only wanted to compare 2 algorithms. The first is, well, what we actually wrote about in this paper that had quite a few nice tricks with valid inequalities and extra bound reduction and stuff like that. And then the second is exactly the same algorithm plus the spatial branching using the delta tilde estimate that I just showed you. And well, 2-hour time limit. I implemented this in both Express and CPEX, and the results are relatively similar. So I'll just show you the results in Express. Well, this is the first table. First, well, you may notice that there's like a 1 order of magnitude improvement in branch and bound time. So if you just look at the branch and bound time, which is the second column of each group, it's basically, well, maybe not 10 times better, but more or less there. To me, the most striking thing, however, is that in terms of branch and bound nodes, there's like a 2 order of magnitude improvement. So this is even more important. So there is a really smaller number of branch and bound nodes that are explored if we carefully chose the GJ variables instead of going through the Z variables. These are the standard instances we looked at the beginning. In the other paper, there were also another few instances that were subdivided in classes, and then I can show you later in the separate in the Q&A what these classes correspond to. But for some of those, actually the classical branching, so the previous algorithm worked a little bit better. For some, instead, for the class 3, I mean none of them for the classical approach got solved within the time limit. And in our case, we took like what, 6 seconds to 12 seconds, something like this. To me, this is really strange because the algorithm itself is relatively simple. It's really just about branching on continuous variables. If I didn't convince you, let's go to the second application. So I tried something similar with another problem that can be modeled with mixed integer convex optimization, and that's a problem of clustering points. So we are given again a set of points. I'm going to change the notation, sorry. So the points are now so the data is now expressed by points in RD. So indeed, I'm n points in RD. There a vector of coordinates is called A1, A2, etc. until AN. We want to subdivide them into K clusters. So K is also given. And we want to find centroids. So these are the true variables of the problem. We want to find K centroids so that they minimize well, the distance between every point to the closest centroid. So this is easily expressed by this objective function you see here, where the norm is a Euclidean norm that can be elevated to the pth power, where p can be 1. or P can be 2. I think I'm running almost out of time, so I'll just speed it up here. So depending on P, you just have two slightly different solutions, the denominations of the problem. I'm gonna skip a few steps here because my time is up. But basically, the classical representation is an MISOCP, so a mixed integer second order cone problem with extra variables that are the binary variables for assigning the points to every cluster, and then some extra variables to compute the actual objective function with whatever value of P you have. What we tried here is an even easier and even simpler branching rule where we were branching on the fundamental variable here, the x, because that's the only real variable and it's continuous, the only variable that actually matters. And if we did this with a very simple branching rule, and let me remind you, we also add the strength and big M constraints because those are the ones that drive the computation of the objective function. What we get is, again, without strong branching, sometimes we were getting much worse results than with this very simple spatial branching. So I meant to say spatial branching before. Without spatial branching, sometimes we reach the time limit, sometimes instead we didn't. And with spatial branching, we were in a few instances we were actually getting much better bounds and much better CPU times. I'll stop here. Thank you very much.
Thank you, Pietro. So we have time maybe for one quick question. If there are otherwise we can move them to the breakout room at the end. But yeah, if there's one quick question, we have 1 minute. Okay, so let's.
I have a quick question.
You go.
Well, I always have one. I was hoping that the audience could go.
I was checking the chat.
So when you say adding the strength and big M constraints, are you replacing them because they're actually strictly stronger, or are you adding them in?
No, I think with most solvers, you can't really modify the current coefficient matrix, so you add them as cuts. That's what I was doing. I mean, probably the solver was recognizing that these cuts were stronger than the original constraints, so was probably removing the original constraints. But I just add them as cuts.
And that could be a lot of big M constraints in general throughout the tree.
Oh yeah.
So do you do some kind of?
No, I leave it to the solver because the solver has, I mean, most solvers have a decent, actually a very good cut pool manager. So I give it to them. A good cut pool manager probably realizes that for at least a given node, there are some constraints that are dominated by others. So these are eliminated and not enforced in the node solve.
Okay, but you could manually also, I guess, if you have a child, the big M constraints you added before are no longer might be strengthened when you branch now once more.
And that's correct. So the deeper you go through the branch and bound tree, the tighter the constraints. So they are dominating. But replacing them from a data structure point of view, I don't think it's possible. So I don't think the API allows you to actually replace constraints, original constraints in the problem, or even cuts in the problem. I'm not entirely sure of that though.
Thank you.
There's a question in the chat. Do we have well, we can do one question, right? I can read it to you if you want. So
sure.
Yeah, maybe
just one, and then we move on to just one. Okay. So MIPLib 2017 has several support vector machine models that are open or hard to solve. Did you try those models, or do they somehow not match the model formulation you used in your presentation?
I wasn't not even aware of these MIPLib instances, but I'll try them out. Can you confirm it's MIPLib 2017?
That's what's written in the chat. Ed, can you confirm that it's?
Yeah, I will give you the link to the specific models there in the chat. as we move on.
Sounds good. Thank you.
Sure.
I'll try them.
Perfect. Thank you very much. Well, the question was fast.
Yes, and thank you, Pietro, one more time.